Let's start lecture 36, and the course is corrosion protection methods, and we will continue our discussion on this broad topic, which is change in electrode potential and associated corrosion protection. Last lecture we actually discussed the differences between anodic protection and cathodic protection. In fact, we also discussed about the kind of initial spike in the current requirement for anodic protection, and then later it reduces to a great extent. So, that initial spike in the current value, so if we have some data, then it will be very easy to appreciate, isn't it? So, let us look at that part, and then we will try to see the differences between cathodic protections, the two things, that is, one is ICCP, another one is sacrificial anode. We will see some of the differences, and then we will try to find out some calculations that what would be the current output if we talk about magnesium anodes or zinc anodes, and then we can also try to look at what could be the number of electrodes or number of anodes that will be required for effective protection to the cathode in case of sacrificial anode situation. Okay. So, let us look at some of the spikes in the current, and then the sudden decrease in the current density once E protection, that the protection potential which is corresponding to the passive range, then we will see that the current requirement would be really low. Okay. So, now let us look at those values, some of the values. So, if we consider that goes to the throwing power. So, for anodic protection, so we will talk about anodic protection. Let us talk about some data for austenitic stainless steel, austenitic SS, and this is nothing but 304, which is nothing but around 18% chromium and 8% nickel, that is the range, and at 30 degree. So, I am taking some data from the book Corrosion Engineering by Fontana and Green. Fine. So, it says that we can have a sense that what could be the corrosion rate that we can experience when it is unprotected and when it is protected. Okay. So, that gives us some idea. So, let us say if it is solution, this is, let us say, solution or electrolyte, and let us say the corrosion rate here. Now, when it is not protected and when it is anodically protected, now if we talk about one normal H2SO4, and this is at 30 degrees Celsius plus 10 to the power minus 5 molar NaCl. When it is unprotected, that means if we talk about the plot, so let us say this is my protection potential. Initially, this is my I core, which is like unprotected system. Unprotected. Now, once it reaches to this level, I can say this is protected. That is the difference between not protected and this is let us say this is anodically protected. So, this is anodically protected and this is unprotected or non protected, not protected. Now, that time its corrosion rate is this corrosion rate is basically MPY 14 and here it is 0.025. So, now you can sense that what is the degree of decrease in corrosion rate once we go to anodic protection. Now, one more example we can cite like 10 normal H2SO4, increasing the strength of it and also increasing the molar percentage or molarity of NaCl, 10 to the minus 3 mole NaCl. Interesting is the unprotected situation, it will be huge corrosion rate, but when it is protected, that time corrosion rate boils down to 0.04 MPY. You can convert this MPY to millimeter per year. So, generally when we talk about MPY in terms of, if we know current density I core, that multiply with atomic weight, this is atomic weight, or let me put it in term with units, I core, which is ampere per centimeter square, let us say, into which is atomic number in terms of gram, then I can put N F rho. Okay. So, this is N is basically the, for example, if we consider M is the metal which is dissolving and any electron which is taken out to dissolve 1 mole of one atom, one metal ion. Okay. So, that time this N is considered here. So, that means for dissolving 1 mole of metal we need NF number of electrons. NF would be the charge, not that N number. So, N into Avogadro number, that will be the number of electrons would be required. For dissolving 1 mole of M. So, and we know 1 mole of 1 Avogadro number or 1 mole of electron is equivalent to 1 Faraday charge, which is nothing but 96500 coulomb. Okay. And the rho is in terms of, so F is in coulomb into rho, which is density gram per centimeter cube, let us say. So, these is I think a general corrosion rate expression when we know this value. Now, this can be mentioned in terms of milli-inch per year. This can be also mentioned in terms of millimeter per year. Okay. And that relation we can indicate that relation. So, we can convert this particular corrosion rate in terms of milli-inch per year, which is nothing but MPY, or millimeter per year. Only thing is this distance unit should be converted into milli-inch or millimeter. Now, if we talk about 1 milli-inch or mils per year, it can be written in terms of 0.025 millimeter per year. Okay. So, this is a conversion, you can do it by putting all those conversion, you can get this. So, now you can now coming to the part that the kind of improvement in corrosion resistance or enhancement in corrosion resistance what you sense when it is unprotected and when it is protected. So that's pretty good actually, and so that means, and interestingly, when you talk about these values, these protected values, it will be almost close to IP. We'll see that data, couple of data will just show, and then we'll show that particular actually this particular anodic protected corrosion rate is almost equal to the corrosion rate what you can calculate by putting IP in place of ICOR. Okay. Now, if we talk about current requirement, in case of anodic protection, let us say if we talk about fluid, and this is also data is taken from the book Corrosion Engineering by Fontana and Green. So, this if we talk about fluid and concentration, then if we talk about temperature, so this temperature is mentioned in terms of Fahrenheit. Okay. Then metal, current density, the maximum current density required to passivate, and of course, uh, to maintain, if we talk about this is to passivate, and current density which is needed to maintain that metal in that protection zone, as we have shown here. So, we have to maintain that particular metal within this zone. Within this zone, if we maintain, then definitely we can get a very low current density. Now, if we talk about couple of examples we can give, like if we consider H2SO4, 1 molar H2SO4, temperature around 75 degrees Fahrenheit, metal is 316 SS. So, that means it contains molybdenum along with chromium and nickel. To passivate, we need around 2100, and here the current density is mentioned in terms of milliampere per feet square. Okay, you can convert in terms of microampere per meter square or ampere per centimeter square. You have to just convert those units into the distance unit or the length unit is to be converted into meter or centimeter, then you will get that. But this value is very high when you consider this 2100 milliampere per feet square. To maintain it needs hardly 11 milliampere per feet square. So, you can sense that the amount of current required to maintain at E protection is very, very low. Then we can think about one example like let us say 45% H2SO4, and when you talk about temperature, if we increase temperature, most of the time corrosion rate increases. Now, this is in case of 304, which is austenitic stainless steel, 18 chrome and 8 nickel. So, that time the current value that is required for passivation, the maximum current that will be needed is 165,000, a milliampere per feet square. It's a huge amount of current. Now, once it reaches to E protection, that value goes to 830, which is very low compared to this. Now, let us talk about some other acids, or let us say base. Let us consider one base, let us say NaOH, and let us talk about 20% NaOH. Temperature is 75 degree Fahrenheit, and we are talking about 304 SS. These are all stainless steel. So, there the current requirement initially for taking it to the protection zone is around 4400 milliampere per feet square. Now, once it reaches to E protection, then it will be around 9.4 milliampere per feet square. So, there are lot many data in that book, you can look into it, but what we would like to say that the current requirement drops drastically once it reaches to the passive range. And interestingly, this current value is almost equal to I passive or IP. Now, what is IP in this particular diagram? IP is basically this, and now why it becomes equal to IP? So, this difference is basically I applied, and here in this particular this value what we are talking about, this is nothing but I applied. Okay, that means I applied means IA minus IC, and in this very diagram this indicates IC, this indicates IA, and since it has gone to anodic polarization segment, so that means we are going from this to this, we are taking it towards positive direction, the potential. So, here IP is on the right, so IP I applied would be equal to IA minus IC, and since IC has a negative sign, so that is what we are taking it as a mod, only magnitude we are considering. Now, IC is so low, so let us say IA is around 11 milliampere per feet square, and let us say this IC value is, let us say this is IA, IC value let us say 10 to the power minus 5 milliampere per feet square. So, this value would not influence the difference, okay, but the difference would be this particular current density, which is IC, could be insignificant compared to IA. So, that is what I applied is actually equal to IP. That is what I was trying to indicate. So, this is about anodic polarization, some of the characteristics, and also its very direct measurement of corrosion rate, okay, or the protection. In case of cathodic protection, we simply say that this is the potential minus 850 millivolt criteria with respect to copper sulfate, the Nasse criteria, that if the potential or the polarization potential of the metal or the steel in soil goes below minus 850, that means it should not go up. So, it should not be like minus 750 millivolt with respect to copper sulfate, then it will not get proper protection. But if it goes around, let us say minus 900 millivolt with respect to copper sulfate, definitely it will have lot of protection, because that is actually taking the potential far below the open circuit potential of iron in that particular electrolyte. So, that is the point we say with respect to polarization we talk about, and we empirically say that if we send this much of current, then let us say we give some amount of current where current output which is going towards steel in case of sacrificial anode or in case of ICCP. So, then we say that it gets sufficient protection, but it does not indicate the direct corrosion protection or direct corrosion rate what that material would experience or the steel would experience during protection. But in case of anodic protection, it is very direct. That means, we know what could be my corrosion rate when it has reached to the protection point. Now, we can talk about some differences between cathodic and anodic difference between ICCP and let us talk about differences between two modes of protection in case of cathodic protection. So, we have two modes like ICCP and sacrificial anode. See, if we try to look at those differences, we can just pinpoint those differences, some of the differences, and it will be but from the design aspects only we can say that the one differences is in one case we need external power source, in another case we need no external power source, but there are some other differences. So, let us talk about that. Differences ICCP and sacrificial anode. Now, if we talk about that, in this case external power source. But here we do not need no external power source. Of course, in this case it has to be DC. This will be little costlier than sacrificial anode mechanism, or we can simply say costlier, and this is cheap. Third is here it is very easy to install, easy installation or easy setup. This is complicated compared to sacrificial anode. Now, if we consider another difference, here we know that stray current problem is little less, but here stray current problem more problematic, it means here the field would be much more heavy than compared to sacrificial anode case. Now, one important aspect is here driving potential is fixed. For example, if we consider minus 850 millivolt criteria with copper sulfate electrode, let us say this is my steel potential under polarized condition, and we know for zinc, which is the anode, that potential would be 1.1 or 1100 millivolt with respect to copper sulfate under OCP condition. So, then the driving potential would be 1100 minus 850. So, which is close to around 250 millivolt, fine. So, this is fixed once we fix the zinc, but here we can actually have driving potential can be varied. In fact, in this case, in case of ICCP, let us say we can actually increase the DC power source rating, or we can actually operate at a low value. It depends, is a variable DC power source we can employ, and that can actually enable us to control the potential requirement or the current requirement during different seasons, or if the soil resistivity changes, then we can definitely control by changing this driving potential, which is controlled by the the external power source which can be variable. Now, these are some of the aspects, of course, on the economic. These are some of the differences between ICCP and sacrificial anode. Okay. So, now finally, it comes to some of the calculations like current requirement or current output when we use magnesium or when we use zinc, as well as we can also calculate the number of anodes that will be required, and then we can also calculate what could be the weight of anodes that will be required and how long that could give protection, number of years. So, those calculations we can do, and that we can take up in our next lecture. At the same time, we will also talk about the characteristics of different anodes like auxiliary anode, and then in case of sacrificial anode we can talk of we can discuss the compositions as well as why those modification in composition is required. Why the modification in composition of those anodes that is required, we'll start discuss in our next lecture. Till then, thank you.